You think the speed of light is just a number, 299,458 meters per second. Fast, really fast, the fastest thing we know. Fine. But why is it the limit? Why can't you go faster? What stops you? What invisible wall slams shut the moment you try to push past it? Most people have never really thought about this. They just accept it. Einstein said so. Speed of light is the cosmic speed limit. That's just how it is. But that's not an answer. That's just repeating words. It's intellectual surrender dressed up as knowledge. When you really ask why nothing can go faster than light, when you dig into what's actually stopping you, when you refuse to accept comfortable half-truths, you discover something so strange, so fundamentally different from everyday experience that it changes everything you think you know about space and time. The speed of light isn't just a speed. It's not just the fastest thing. It's the architecture of reality itself. It's woven into the fabric of space and time in a way that makes going faster literally meaningless. Not impossible in the way that climbing Mount Everest barefoot is impossible, but meaningless in the way that asking what's north of the North Pole is meaningless. Let me show you what I mean. If you've never questioned this before, you're not alone. But now that you're seeing it, there's no going back. Once you understand what the speed of light actually represents, you'll see it everywhere. In every GPS satellite, every particle accelerator, every ray of sunlight warming your face. And you'll wonder why most people still don't get it. You'll wonder how you went so long without truly understanding. Let's start with something simple, something everyone knows, something so mundane you've never given it a second thought. Things fall. Drop something, it falls down. 16 feet in the first second, to be precise. That's what Galileo measured in the 16th century, rolling balls down inclined planes, timing them with his pulse, revolutionizing our understanding of motion with nothing but patience and curiosity. Drop a ball, drop a rock, drop anything. In 1 second it falls 16 feet. Now consider the moon. The moon is going around the Earth. It's not falling down. It's staying up there orbiting, going in a circle, seemingly defying the very gravity that pulls everything else to the ground. But wait, is it falling? Think about it. If the moon were just sitting there in space, not moving, completely stationary, what would happen? It would fall toward the Earth. Gravity would pull it in, just like it pulls an apple from a tree. But the moon is moving. It's moving sideways, tangent to its orbit, perpendicular to the line connecting it to Earth. And because it's moving sideways while gravity pulls it down, it keeps missing the Earth. It falls toward the Earth but keeps missing. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. The moon has been falling for 4.5 billion years and hasn't hit the ground yet. Now, here's where Isaac Newton had his brilliant insight. The moon is 240,000 miles from the center of the Earth. We're standing on the surface 4,000 miles from the center. So the moon is 60 times farther away than we are. Newton said, what if gravity gets weaker with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker. 3 times as far, 9 times weaker. The square of the distance. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. Now on Earth, things fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the math. 16 feet divided by 3,600. That's about 1/20th of an inch per second squared. Newton calculated how far the moon should fall toward Earth in 1 second if gravity follows an inverse square law. And it matched perfectly. The moon is falling at exactly the rate Newton's law predicts. The same force pulling an apple to the ground is pulling the moon around the Earth. This was huge. This wasn't just a theory. This was a prediction that connected the mundane to the celestial. Newton took a completely independent fact, how fast things fall on Earth, and connected it to another completely independent fact, the period of the moon's orbit and its distance from Earth. Two things that seemed totally unrelated, one measured in orchards and the other measured by astronomers staring at the night sky, suddenly became connected by one law, the law of universal gravitation. There was no going back. The universe revealed itself to be comprehensible, unified, governed by principles that apply everywhere. Now Newton went further. He calculated what the shape of planetary orbits should be if gravity follows an inverse square law, and he found that it should be an ellipse. And guess what? Planets do move in ellipses. Johannes Kepler had already measured that decades earlier, painstakingly analyzing Tycho Brahe's astronomical observations. But Kepler didn't know why. He had the pattern but not the explanation. Newton explained it. He got 3 for 2, as it were. One law explaining multiple phenomena. And then more things fell into place. The tides. Why are there tides? Because the moon pulls on the Earth. But wait, if the moon just pulls the Earth toward it, there should only be one high tide per day, right? The bulge of water on the side facing the moon. But there are 2 tides per day, roughly every 12 hours. Why? Some people thought the Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both were sort of right, but neither got it completely. Newton realized what was really going on. The force of the moon on the Earth and on the water is the same at the same distance, but the water on the near side is closer to the moon than the center of the Earth is. So it gets pulled more. And the water on the far side is farther from the moon than the center of the Earth is. So it gets pulled less. So you get 2 bulges. One where the water is pulled more toward the moon, one where the water is left behind, because the Earth is pulled more than that distant water. 2 tides per day. The Earth does the same trick as the moon, both orbiting their common center of mass. The tides were explained, and the fact that there were 2 a day. A lot of other things became quite clear. Why the Earth is round, because everything gets pulled toward the center. Why it isn't perfectly round, because it's spinning, so the equator bulges out a little as the rotation throws material outward. Why the sun and moon are round, and so on. Now, as science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent and revealing. The first careful tests involved the moons of Jupiter. By careful observations of how they went around over a long period of time, one could check very carefully that everything was according to Newton's laws. And it turned out not to be the case. The moons of Jupiter appeared to get sometimes 8 minutes ahead of schedule, and sometimes 8 minutes behind schedule, where schedule means the calculated values according to Newton's laws, 8 minutes. That's a huge discrepancy for precise astronomical observations. Something was wrong. But wait. It was noticed that they were ahead of schedule when Jupiter was close to the Earth and behind schedule when Jupiter was far away. Rather odd circumstance. Avmer, having confidence in the law of gravitation, came to an interesting conclusion. It takes light some time to travel from the moons to the Earth. And what we're looking at when we see the moons are not how they are now, but how they were some time ago, the time it took the light to get here. When Jupiter is near us, it takes less time for the light to come. When Jupiter is farther, it takes longer. So he had to correct the observations for the differences in time, and by the fact that they were this much too early or that much too late, he was able to determine the velocity of light. This was the first demonstration that light was not instantaneously propagated. Light had a speed, and that speed was finite and measurable. Think about what just happened. We found the speed of light not by measuring light directly, but by having confidence in the law of gravitation. When something didn't match, instead of throwing out Newton's law, Avmer said, "What if light takes time to travel?" And he was right. I bring this particular matter to your attention because it illustrates something profound about how science actually works. When a law is right, it can be used to find another one. By having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries, each new discovery providing tools for much more discovery. Now, here's where it gets uncomfortable. You're realizing that everything you thought you knew about the universe was built layer by layer, each insight enabling the next, each mystery resolved opening 3 more. That feeling, that mixture of excitement and frustration, that's growth. That's your brain rewiring itself to accommodate deeper truth. How many other things do you accept without questioning? What else is hiding in plain sight, waiting for someone to ask the right question? This beginning of that avalanche has gone on now for 400 years in a continuous process, and we're still avalanching along at high speed at this time. But here's the thing that changes everything. Once you know the speed of light, once you measure it, you start noticing something very, very strange. Light always travels at the same speed. Always. No matter who measures it. No matter how fast you're moving. No matter which direction you're facing. No matter where you are in the universe. Let me make this concrete. You're standing still on a train platform. You shine a flashlight. You measure the speed of the light coming out. 209.92, 458 meters per second. Fine. Exactly what you'd expect. Now you get on a train. A fast train, moving at half the speed of light relative to the platform. You shine the flashlight forward in the direction the train is moving. Common sense says the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward from a moving train, the ball moves faster relative to the ground than if you threw it while standing still. Velocities add. That's basic physics. But that's not what happens with light. You measure the light and it's still traveling at 299, 792, 458 meters per second, exactly the same speed. Not faster, the same. You say, okay, maybe I measured wrong. So you get the train going even faster, 90% the speed of light. You shine the flashlight forward again. You measure still 299, 792, 458 meters per second. You get frustrated because this makes no sense. You get the train going at 99% the speed of light, so close to light speed that you can almost touch it. You shine the flashlight. You measure still the same speed, always, forever, unchanging. The speed of light does not add to your velocity. It doesn't combine with your speed. It's always the same no matter how fast you're moving, no matter what reference frame you're in. This should break your brain. This is not how speeds work in everyday life. Speeds add. If you're on a train moving at 50 miles per hour and you walk forward at 3 miles per hour, you're moving at 3 miles per hour relative to the ground. That's Galilean relativity, and it works perfectly for everything we experience in daily life. But light doesn't obey it. Light always moves at the same speed relative to you, no matter how fast you are moving. Why? Albert Einstein realized what was going on, and it's so strange, so contrary to common sense, so violently opposed to our intuitions that even now, over a century later, people struggle to truly accept it. Time and space are not fixed. They're not the unchanging stage on which events occur. They're flexible. They bend and stretch to keep the speed of light constant. When you move faster, time slows down for you. Your clock literally ticks slower, not because it's broken, not because of some mechanical effect, but because time itself passes more slowly for you, and distances contract. The space in front of you gets compressed, shortened, squeezed. These effects are real. They are not optical illusions. They're not measurement errors or tricks of perception. Time actually slows. Space actually contracts. And the amount they change is exactly the right amount, precisely calculated by the Lorentz transformation equations to make the speed of light come out the same for everyone. Let me say that again because it's so important. The universe adjusts time and space, bends them, stretches them, compresses them, all to ensure that light always travels at the same speed for everyone. The speed of light is not just a speed, it's a structural constant of the universe. Space and time are arranged in such a way that this speed is the same for every observer, regardless of their motion. The universe conspires across all of reality to preserve this one number. Now, here's where it gets even stranger, where the implications cascade outward like ripples in a cosmic pond. If you try to accelerate something, anything with mass, to the speed of light, something very weird happens. The closer you get to the speed of light, the harder it becomes to go faster. It's not that you run out of fuel. It's not that your engine isn't strong enough or that you need better technology. It's that the object itself resists acceleration more and more. We call this relativistic mass increase, though physicists prefer to talk about it as an increase in inertia. As you go faster, it becomes harder and harder to change your velocity. And as you approach the speed of light, your resistance to acceleration approaches infinity. To actually reach the speed of light, you would need infinite energy, which is by definition impossible. So nothing with mass can ever reach the speed of light. Not because of some arbitrary rule written in a physics textbook, not because of engineering limitations we might someday overcome, but because the structure of space-time itself prevents it. The very fabric of reality says no. Light can travel at that speed because photons have no mass, zero. None. Massless particles can travel at the speed of light. In fact, they must. They have no choice in the matter. They're always moving at that speed, never faster, never slower. But anything with mass, an electron, a proton, a spaceship, you can get close. Very close, 99% of the speed of light, but never quite there. The universe won't let you, and it's not holding out on you. It's showing you something fundamental about how reality is constructed. We're about to connect everything. But before we do, ask yourself, are you the kind of person who actually follows through? Who takes knowledge and does something with it? Because what comes next isn't just information. It's a lens that will change how you see everything. Every time you look at a beam of sunlight, every time you use a GPS, every time you contemplate the stars, you'll understand what's really happening beneath the surface. And you can't unsee it. Now you might ask, but why? Why is the universe set up this way? Why is there a speed limit at all? And here's the answer that's going to frustrate you. There isn't a deeper why. Not in the sense you're hoping for. The speed of light isn't a speed limit imposed on the universe from outside, like a traffic law written by some cosmic legislator. It's a consequence of how the universe is structured at its most fundamental level. Space and time are not separate. They're woven together into a single entity called spacetime. And spacetime has a geometry, a structure, a shape that determines what's possible and what isn't. That structure has a built-in conversion factor between space and time, a fundamental constant that relates distances to durations. That conversion factor is the speed of light. It's not that light is special. Light just happens to travel at this fundamental rate because light has no mass. But the rate itself is a property of space-time, not of light. If light didn't exist, the speed limit would still be there, embedded in the architecture of reality. It's a feature of the universe itself, as intrinsic as the fact that space has 3 dimensions. Here's another way to think about it that might make things click. In everyday life, you think of space and time as separate things. You move through space. Time passes. They're independent, like 2 different channels you can tune separately. But they're not. This is the insight that changes everything. You're always moving through space-time at a constant rate. Always. Every moment of your existence. But that motion is divided between space and time. If you're sitting still, not moving through space at all your motion is through time. You're moving into the future at the maximum possible rate, 1 second per second. Your clock ticks normally. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through both space and time, which means you're moving through time more slowly. Your clock ticks slower. The faster you move through space, the slower you move through time. It's a trade-off, a cosmic budget that must always balance. And there's a maximum. If you could move through space at the speed of light, you would have 0 motion left over for time. Time would stop for you completely. Your clock would freeze. This is why light doesn't experience time. From a photon's perspective, it's emitted and absorbed in the same instant. No time passes at all. The universe is frozen, a single eternal moment. A photon emitted from a star 8 billion light years away experiences no journey, no waiting, no duration. From its perspective, emission and absorption are simultaneous. You can't go faster than light because you can't have less than 0 motion through time. That's the limit. That's the wall. And it's not arbitrary. It's geometrical, built into the very structure of how space and time relate to each other. So now what? You've just spent these minutes fundamentally changing how you understand reality. That's not nothing. That's rare. Most people never have this experience, never push past the comfortable explanations to see what lies beneath. The question is, will you remember this tomorrow, next week, or will it fade like everything else you've learned and forgotten? There's a way to make sure it sticks. There's a way to prove to yourself that this mattered, that you're not just passively consuming information, but actively engaging with it. And here's the beautiful part. This isn't just theoretical. It's not philosophy dressed up as physics. We've tested this over and over and over, with increasing precision and in countless different ways. Particles in accelerators get accelerated to 99% the speed of light. And guess what? The closer they get, the harder it becomes to accelerate them further. Their resistance to acceleration increases exactly as Einstein's equations predict. Not approximately, not roughly, but exactly. GPS satellites have to account for time dilation. They're moving fast relative to us on the ground, and they're in a weaker gravitational field. So time passes differently for them than for us. If we didn't correct for this relativistic effect, GPS would be off by kilometers within a single day. Your phone's maps would be useless. The fact that GPS works at all is daily confirmation that Einstein was right. Muons created in the upper atmosphere by cosmic rays should decay before reaching the ground. Their half-life is about 2 microseconds. Even traveling at nearly the speed of light, they should only make it about 660 meters before most of them decay. But the upper atmosphere is much higher than that. Yet we detect huge numbers of muons at ground level. How? Because they're moving so close to the speed of light that time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer than stationary muons because they're moving fast. Either way you calculate it, more muons reach the ground than classical physics would predict, exactly as relativity requires. It's not speculation, it's measured. Verified, confirmed. The speed of light being a limit is as well tested as anything in physics, as solid as the ground beneath your feet. So let's bring this all together. Why is the speed of light the limit? Because space-time is structured in a way that has a maximum rate at which cause and effect can propagate, a maximum rate at which information can travel, a maximum rate at which anything can happen. That rate is the speed of light. Not because light is special, but because space-time itself has this built-in conversion factor between space and time. You can't go faster because going faster would require moving backwards through time, which doesn't make sense within our universe's geometry. You can't have negative time. You can't undo cause and effect. The speed of light is the speed at which now propagates through the universe. It's the edge of the possible, the boundary between what can happen and what cannot. And this process, this avalanche of discoveries, started with Newton figuring out gravity by watching an apple fall and thinking about the moon. Then Armour figuring out the speed of light by watching Jupiter's moons and trusting Newton's equations. Then James Clerk Maxwell unifying electricity and magnetism and finding that electromagnetic waves travel at the speed of light. Then Albert Michelson and Edward Morley trying to detect Earth's motion through the supposed luminiferous ether and finding nothing. Then Einstein realizing that the speed of light is constant and deriving special relativity from that single postulate. Then thousands of experiments confirming it, refining it, testing it to 18 decimal places. Each discovery building on the last. Each new insight opening doors to more insights. That's how science works. That's the avalanche that's been going on for 400 years. And we're still avalanching along at high speed at this time. If you made it this far, you're part of a small group. The group that doesn't settle for simple answers. The group that wants to understand, not just know, not just repeat what they've been told. And here's what I've learned, people like you, people who think like this, who push past the surface to see the machinery beneath, they find each other. They recognize each other. They build on each other's understanding. That's how the avalanche continues. That's how we keep discovering. Not alone, but together. Each generation standing on the shoulders of the last. The speed of light isn't just a number in a physics textbook. It's the key. It's the thing that unlocks how space and time work, how they're woven together, how they bend and stretch and flow. It's the thing that shows us the universe is stranger and more beautiful than we ever imagined, more alien to our intuitions than any science fiction could capture. And the fact that we can understand it, that we can measure it, test it, use it to make predictions that turn out to be true, that we can glimpse the deep structure of reality through careful thought and observation, that's the beauty of physics. Not comfort, not simplicity, truth.